So let's learn about matrix operations. So first of all, here's some notation I'm going to use. I'm going to use capital letters for matrices typically. So if A is a matrix with M rows and N columns, the rows are horizontal. So this is like if I say it M rows, that's like the height of from top to bottom of the matrix. And N columns, that's the width of the matrix. So we say that A is M by N, so that's the height by the width. The first number is height, second number is width. Or sometimes it's like M times N. Like this just means, means the same thing. We write A sub ij. There's two subscripts. The first subscript tells you what row it is, and we count from top to bottom. So the top is the first row and so on. And the second subscript tells you which column it is, and we go from left to right. Okay, so here's some basic operations. Scalar is just a number, like in Calc 3, you probably use the word scalar this way. Scalar could be a real number, it could also be a complex number. Maybe for right now, let's just say it's a real number. If I take a scalar times a matrix, that just means it's a really easy operation. I just take this scalar and multiply every single entry of the matrix by that scalar. So, it's really easy, but let's do an example. Say I've got 2 times this matrix, I'm going to multiply every single entry by 2. It's that easy. Okay, we are going to eventually get to an operation that is not easy, but first here's another one that's easy. Matrix addition. If A and B are both M by N, and keep in mind they have to be the same dimensions for this to work. So if they have to have the same height and the same width. If they don't have the same height or the same width, then we just say A plus B is not defined. So assuming they have the same height and width, we just add going across. Like I'm going to write A plus B equals C, where any entry of the matrix C is just obtained by adding the 2 corresponding entries of A and B. So this is another easy one. By the way, C is going to have the same dimensions as A and B, so if this is 2 by 2 and this is 2 by 2, then C is going to be 2 by 2. And so to get the top left entry, I just add the top left here and the top left here. So 4, and to get the top right entry, I just do this plus this, 2 plus 0, 0 plus 1, 1 plus 2. Very easy. What makes these easy is sort of the position. Like if I'm wondering what to put here, then I'm thinking about its position. I'm thinking about the lower right, and so I just look at the same position here and the same position here. For the operation we're about to learn, matrix multiplication, it's not truly hard, but you have to pay a little bit more attention to what you're doing. So let me try to explain this. First of all, there's something funny about the dimensions. I'm going to talk about A times B, and for this to work, A should be, it should have some dimension, say M by N, and B should be N by P. What's important is that this N is the same as this N. In other words, the number of columns in A, that's this N, and the number of rows in B is the same. So, in other words, just to go really slowly, the width of A and the height of B is the same. So, otherwise we say the product is just undefined. So, assuming that it's the same, the number of columns of A and the number of rows of B is the same, then here's how we do the product, A times B. This is a formula for it. This is maybe not the most easy to understand, so let me explain sort of more mechanically or visually what you do. If I want the C sub ij, so if I want the matrix, the A times B is going to be C, and C is going to be a matrix. And if I want the entry in the ith row and jth column of C, here's what I do. I look at the ith row of A, which is the same row as the entry of C that I'm looking at. So I look at that row of A, and then I look at the jth column of B, which is the same column as the entry of C that I'm looking at. This is the jth column of C, so I look at the jth column of B. So I look at the appropriate row of A and column of B, and then it's like I do a dot product going across this and down this. And when I say dot product, of course I mean this number times this number plus this number, the second number times the second number, plus the third number times the third number, all the way until I get to this last number times this last number. The reason why the width of A has to be the same as the height of B is so each one of these numbers has a partner to match up with, because I'm going to do the first one times the first one, the second one times the second one. There needs to be the same number going across here as going down here, or else not everything will have a partner to get multiplied by. And right, of course, what I just described, if you look back up at the formula that I wrote, that is the same thing. I'm doing this number times this number, that's this, and then the second one times the second one, that's this, all the way down. Right, so if you think about it, the dimensions of C are going to be M by P. The number of rows of C is the same as the number of rows of A, which is M. And the number of columns of C is going to be the same as the number of columns of B, which is P. Let's do an example. So these bubbles are not really necessary, but I like to draw them because we're going to go across the rows of the first matrix and down the columns of the second matrix. So let me fill in the product here. So if I want the top left entry, here, let me just put a box here. If I want the top left entry, that means I look at the top row of the first matrix and the left column of the second matrix. And I'm going to go across, like I'm doing a dot product. So I'm going to get, here, for the first one, I'll write all my work. First number times first number, second number times second number, third number times third number. I do all that work just to fill this in. So 0 plus 0 plus 1, and the result goes here. Okay, so I'll show less work on the rest. For this one, I'm looking at the top row and the right column. So I've got a 3 plus a 0 minus a 1. So that's all, that all adds up to 2. For this, I'm now looking at the bottom row, left column, so 2 times, so I've got a 0 plus a 1, and then a negative 1. That's all just 0. And then finally down here, it's the bottom right, so I go the bottom row, right column, so 6 plus 4 plus 1. That's how we multiply matrices. So let me just give a hint of why we do this. Why did we just define this crazy operation? There's a number of reasons. I'll tell you one that's motivated by what we've already done with matrices. So what we use matrices for is solving systems of linear equations. So let me go back to the original way we wrote a system of linear equations, which is like we have these variables x1 through xn, and we have all these equations, and they have different coefficients. So I'm imagining that I have m equations and n variables, and so in each equation I have these coefficients like like a's with subscripts. Those are my coefficients. And I have some numbers on the right side, like b's with a subscript. And using matrix multiplication, I can write the same thing this way. This is the matrix that I get by just storing all these same numbers as coefficients. This is a matrix that just has one column, and the entries of that column are just our variables, x1 through xn. And this is also a matrix that just has one column, and I just put the b1 through bn. This equation, which involves matrix multiplication, that's why I'm putting these right next to each other. So I claim that this equation says the same thing. And, well, why does it? Well, how do I do matrix multiplication? I go across the rows of this and down the columns. Of course, this one only has one column. And so if I wanted, say, the top entry of this, I would go the top row with this column, and I'm doing a dot product, so I do the first number times the first number. So A11 x1, and then the second number times the second number. In other words, I'm just going to get this equation. So that's what I'm telling you, is that this expresses the same thing as this. Okay. Let me go over some properties of the operations that we just talked about. So we talked about three operations: a scalar multiplication, and then adding a matrix to another matrix, and then multiplying a matrix by another matrix. There's a bunch of properties that are sort of what you would think, but it gets a little bit dangerous because there's one important property that one might think would hold that doesn't hold. So first of all, let me go through the ones that are sort of as expected. So we have a distributive property, and by the way, when I use little s and little t, those are scalars, so those are like real numbers or maybe complex numbers. Capital letters like A, B, and C, those are matrices. So we could call this a distributive property. I'm doing scalar multiplication, but then inside the parentheses I'm doing matrix addition. And this is sort of what you would expect just based on what the standard distributive property. Like if the symbols A and B just stood for numbers, then this would be the standard distributive property. But now A and B are matrices. But it says what you would think it would say. Here's a different version of the distributive property, this second line. In this one, I'm adding two scalars and multiplying the result by a matrix. But the result is what you would think. It's, just this times this and then this times this. Here's another version of the distributive property where there's no scalars anymore. That's just matrix multiplication and matrix addition. And it says, well, what you would think. You might wonder why I would write this next one separately, because it sort of looks the same. The reason for writing it separately is because this is, well, it's like multiplying something on the right is not necessarily the same as multiplying it on the left, and that's something that I'm going to get to. So these are two separate properties, but they in general, I would describe them both as distributive properties. This is the associative property. This says that if I want to multiply A and B and C in that order, like A's all the way on the left, B's in the middle, and then C's all the way on the right, it doesn't matter if I multiply A by B first and then multiply the result by C, or if I multiply B times C first and then multiply that on the left by A. So why am I being so careful about multiplying things on the left or multiplying on the right? It's because this is the dangerous property that one might assume should hold, because if A and B are just real numbers or complex numbers, then A times B does equal B times A, no matter what. But when we're talking about matrices, it's not necessarily the case. Sometimes A times B equals B times A, but that's kind of a coincidence when it happens. In general, they're not the same. In fact, they might not even have the same dimensions. Like, we just did an example. This is 2 by 3, and this is 3 by 2, and the result is 2 by 2. But if I were to put this matrix first and this matrix second, the result would be 3 by 3, because it's always the height of the first matrix and the width of the second matrix. So if I put this one first and this one second, then it would be a 3 by 3 result. So there's no way we would get the same answer. They wouldn't even be the same dimensions. So we have to be a bit careful with matrices. When I say A times B, in general, I have to be careful whether I mean A is on the left and B is on the right, or if it's the other way around. So, and hopefully I was careful about the way I talked about these things. I tried to be, but now you know why I was trying to be careful.